Welcome to this comprehensive overview presentation on the network of surface robots with ambient intelligence. Based on the 3GPP Technical Report 22.916, version 19, which was released in December of 2023. This report delves into the intricate world of efficient communication services and cooperative operations for groups of service robots. The concept of ambient intelligence in this context refers to an environment where robots are seamlessly integrated, responsive, and adaptive to human needs. This integration is made possible through advanced networking technologies, particularly those outlined in 3GPP standards for 5G and beyond. Our exploration will cover various use cases that demonstrate the potential of these robotic networks, from industrial applications to smart community services. We'll also address the technical challenges that come with implementing such systems, including issues of network reliability, data fusion, and real-time communication in diverse environments. As we progress through this presentation, we'll examine how emerging technologies like multi-access edge computing, MEC for short, integrated sensing and communication, ISAC for short, and advancements in machine-to-machine communication protocols are shaping the future of service robotics. We'll also touch on the implications of these developments for sectors ranging from healthcare and agriculture to mining and urban planning. Let's begin. Today, I'd like to take you through a comprehensive overview exploration of this exciting field. We'll begin with an introduction to the scope of our study, outlining the key focus areas in service robot communications and operations. This will set the stage for our discussion and provide context for the use cases we'll examine. Next, we'll provide an overview of service robot networks, discussing the fundamental concepts and challenges in this domain. This section will cover important topics such as the definition of unmanned systems, the critical role of communication availability, and the diverse requirements from the robotics industry. The core of our presentation will be an in-depth look at 8 distinct use cases. Each of these scenarios showcases different aspects of service robot networks and highlights unique challenges and opportunities. We'll explore applications ranging from 3D mapping and safety protection to smart communities and mining operations. After examining these use cases, we'll broaden our perspective to consider other important aspects of service robot networks. This includes emerging technologies like tactile communication and integrated sensing, as well as the potential intersections with the metaverse. We'll conclude our presentation by summarizing key findings, discussing common challenges across use cases, and offering recommendations for future work in this field. Let's begin. The scope of this study is multifaceted, encompassing various critical aspects of service robot communications and operations. Here are a few focus areas. We'll go through them sequentially. First of all, I'd like to talk about information exposure between application and communications layers. This involves creating efficient interfaces that allow seamless data exchange between the high-level applications running on robots and the underlying communication infrastructure. For example, this could include mechanisms for applications to request specific QoS quality of service levels, or for the network to provide real-time status updates to applications. And then support for on-demand high-priority communications. In scenarios where immediate action is critical, such as emergency response or safety-critical operations, the network must be able to prioritize certain communications over others. This might involve techniques like network slicing or dynamic QoS adjustment. KPIs for large-scale group operation scenarios are all about defining and measuring KPIs, key performance indicators, for robot swarms or large groups of cooperating robots. These could include metrics like swarm cohesion, task completion efficiency, or communication overhead. Regarding scalable and efficient use of communication resources, as the number of robots in a network grows, so does the demand on communication resources. We'll explore techniques for efficient spectrum usage, such as cognitive radio technologies or dynamic spectrum allocation. Requirements for media applications specific to service robots includes considerations for video streaming, augmented reality overlays, or other rich media applications that robots might use or generate. We'll look at factors like low latency encoding, bandwidth efficient transmission, and context-aware compression techniques. As for security, privacy, and charging aspects, excuse me, as robots collect and process potentially sensitive data, robot security measures are crucial. We'll examine encryption methods, secure communication protocols, and privacy-preserving techniques. Additionally, we'll consider novel charging mechanisms that account for the unique usage patterns of robotic networks. Service robot networks represent a complex ecosystem of unmanned systems, UMS in short, each with its own capabilities and communication needs. Let's break down the key components. Definition of unmanned system, UMS in short. A UMS is any robotic system capable of operating without direct human control. This can range from simple automated machines to highly sophisticated autonomous robots with AI capabilities. Importance of communication availability. Reliable communication is the backbone of service robot networks. It enables coordination, data sharing, and remote operation. We'll explore technologies like ultra-reliable low-latency communication, URLLC, in 5G networks, which can provide the necessary dependability for critical robot operations. Collaboration nodes within group operation models. Robots can collaborate in various ways, such as leader-follower models, distributed decision-making, or centralized control. Each model has different communication requirements and challenges. Relevance to 3GPP 5G system support. The 5G system, as defined by 3GPP, offers features particularly beneficial for robotics, such as network slicing, edge computing support, and enhanced mobile broadband. We'll examine how these features can be leveraged for service robot networks. Spectrum usage considerations. Efficient use of the radio spectrum is crucial for large-scale robot deployments. We'll discuss techniques like dynamic spectrum access, cognitive radio, and the potential use of millimeter wave frequencies for high bandwidth, short-range communication. Diverse requirements from robotics industry. Different robotic applications have varying needs in terms of latency, bandwidth, reliability, and coverage. We'll explore how these diverse requirements can be met within a unified network framework, possibly through techniques like network slicing or software-defined networking. Now let's take a look at use case 1. We have 8 distinct use cases here on this presentation to illustrate the topics regarding robotics. So let's examine use case 1. This use case showcases the potential of energy-efficient robots collaborating to create high-resolution 3D maps, with applications ranging from automated cleaning and disinfection to precision agriculture. The key to this system's effectiveness lies in its adaptive capabilities and emphasis on resource optimization. These robots employ sophisticated simultaneous localization and mapping algorithms, SLAM. Remember, we talked about SLAM quite a bit in the previous presentation on ambient intelligence. SLAM stands for simultaneous localization and mapping algorithms, which allow them to build a map of their environment while simultaneously tracking their own position within it. The collaborative aspect introduces additional complexity, as robots must share and integrate their individual map data in real time to create a cohesive, unified 3D map. The system primarily operates using PROSE, which is a short acronym for Proximity Services, a 3GPP-defined technology that enables direct device-to-device communication. This approach reduces network load and allows for operation in areas with partial or intermittent new generation RAN, or next generation RAN, NG-RAN coverage. However, it also introduces several technical challenges. 1. Clock synchronization. Precise timing is crucial for accurate map building. The system employs advanced synchronization protocols, possibly leveraging techniques like the PTP. PTP stands for Precision Time Protocol, or NTP, which is Network Time Protocol, adapted for the unique needs of mobile robotic networks. So these are not new protocols. We use these protocols in our wireless networks a lot, PTP and NTP. Second is the second challenge is network resumption. When robots temporarily lose connection to the network or each other, they need to quickly reestablish links and reconcile any divergences in their map data. This involves efficient handshaking protocols and delta-based data synchronization to minimize bandwidth usage. And then regarding predictive communication, to handle potential disruptions, the system implements predictive algorithms that anticipate communication breakdowns based on factors like signal strength, historical data, and environmental conditions. This allows robots to preemptively adjust their behavior or data sharing strategies to maintain mapping continuity. The system also incorporates edge computing elements to process and fuse sensor data locally, reducing the need for constant high bandwidth communication with a central server. This distributed approach enhances the network's scalability and resilience. Now, there's a diagram here that corresponds to our use case 1. I have diagrams from the spec itself to always follow a description of a particular use case, so it will give us a clear idea what exactly the use case is. So this is for use case 1, online cooperative high resolution 3D map building. This diagram illustrates a use case using a group of service robots with ambient intelligence. The diagram is divided into 2 main parts: intra-robot operation, which is on the left side, and inter-robot operation, that's on the right side. So let's take a look at the intra-robot operation that is on the left side. This section represents the internal processes within a single robot. Policy update and phase-based optimal control. This component is responsible for updating the robot's policies and implementing optimal control strategies based on the current phase of operation. State feedback control. This block receives input from the policy update component and implements control actions based on the current state of the robot and its environment. State estimation. This module estimates the current state of the robot using data from various sensors and previous state information. Sensing / localization. This component gathers data from the robot's sensors and determines its position and orientation in the environment. The arrows between these components show the flow of information and control signals within the robot's internal system. Now let's take a look at the inter-robot operation on the left, on the right side, pardon me, inter-robot operation. This section illustrates how multiple robots interact with each other and the world, and the network, Multi-radio interface. Robots communicate with each other using multiple radio interfaces, allowing for robust and flexible communication. Sharing intent and environmental data. Robots exchange information about their intentions and the environment they're sensing, facilitating cooperative behavior among themselves, among the different robots. 3GPP system. The robots connect to the 3GPP cellular network, which provides access to the network fabric. This allows for broader connectivity and potential access to cloud resources. Look at the Geno Bs. These are the 5G base stations, of course, that provide cellular connectivity to the robots. The edge. This represents edge computing resources that can be accessed through the 3GPP network, allowing for offloading of computationally intensive tasks. Some of the key aspects of this use case reflected in this diagram are the following. Collaborative 3D mapping. The robots work together to build a high-resolution 3D map of their environment, sharing data and processing tasks. Energy efficiency. The intra-robot operations are designed to optimize control and sensing, contributing to energy-efficient operation. Adaptability. The state estimation and state feedback control components allow robots to adapt to changes in the environment. Network integration. The use of 3GPP systems enables the robots to leverage cellular network capabilities and access edge computing resources. Scalability. The inter-robot communication architecture allows for multiple robots to work together in a scalable manner. Real-time cooperation or operation. The feedback loops and state estimation components enable real-time decision-making and control. This diagram encapsulates the key elements of the use case 1, showcasing how a group of service robots can cooperatively build 3D maps while efficiently managing their resources and adapting to environmental conditions. The integration within 3GPP systems highlights the role of advanced cellular networks in enabling these sophisticated robotic applications. Now, let's take a look at use case 2, real-time cooperative safety protection. This use case demonstrates the integration of robotic systems with human security personnel to create a comprehensive area protection solution. The system leverages advanced sensor fusion, real-time data analysis, and coordinated decision-making to enhance safety and security. The key tasks in this scenario include patrolling. Robots use predefined routes and adaptive patrolling algorithms that adjust based on real-time risk assessments and historical data. Target identification and tracking. Employing computer vision and machine learning algorithms, the system can identify and track potential security threats. This involves real-time video analytics, possibly using convolutional neural networks, CNNs, for object detection, and recurrent neural networks, RNNs, for tracking. Intelligent detection. Beyond visual data, the system integrates inputs from various sensors like infrared cameras, acoustic sensors, and motion detectors to provide comprehensive situational awareness. Alarm reporting. When a potential threat is detected, the system must quickly and accurately disseminate this information to all relevant parties. The effectiveness of the system hinges on its ability to share information in real time and make synchronized decisions. This requires low latency communication, utilizing technologies like 5G URLLC, remember URLLC, ultra reliable low latency communication, a term used all the time, to ensure that critical information is transmitted with minimal delay. Synchronous data transmission, implementing time-sensitive networking, TSN. In short, protocols to ensure that data from multiple sources, that is from the robots, sensors, human inputs, etc., arrives synchronously for accurate decision-making. Hierarchical decision-making is a system that employs a flexible leadership structure where decisions can be made by a lead robot, human operator, or a remote control center, depending on the situation and available information. A major challenge in this use case is ensuring that data from multiple sources arrives synchronously, allowing for timely and accurate decisions. This requires precise time synchronization across the network and intelligent data routing algorithms. Additionally, the system must efficiently manage resources with synchronization or when synchronization fails, perhaps by falling back to local decision making or prioritizing the most critical data streams. Now let's take a look at the image for use case 2. This image illustrates the real-time cooperative safety protection use case described on the previous slide. Now let's go through the various components on this diagram, shall we? Robots. Here, the robots, there are 3 robots, each equipped with cameras and sensors. These robots are designed for security protection tasks such as patrolling, target identification, tracking, and intelligent detection. They represent the core of the distributed security system. We have security staff. A human security staff member is depicted carrying AUE user equipment, likely a smartphone or dedicated device. This represents the human element in the security system, capable of making high-level decisions and responding to complex situations that may require human judgment. Communication links. We have side link, SL, sometimes you see SL, that's side link. The dotted lines between robots indicate side link communication. This allows direct device-to-device communication between robots without going through the cellular network, enabling fast local data exchange. Uplink, downlink. The lines connecting robots to the GNOB which is the next generation Node B or 5G base station, represent the cellular network connections. These links allow robots to communicate with the broader network and the security controller. And then we have the G-Node B. Two G-Node Bs are shown representing 5G base stations. These provide cellular network coverage and connectivity for the robots and security staff. They facilitate communication between the ground-level security elements and the cloud-based security controller. Multi-access edge computing, the cloud icon labeled security controller and application function in brackets represents the multi-access edge computing (MEC) component. This is a critical element that processes data from multiple sources, robots, security staff, for example, and making high-level decisions based on aggregated information. It also helps to coordinate the overall security strategy, as well as providing low latency computation and data processing close to the source. In terms of network architecture, the diagram illustrates a hybrid network architecture combining local communication, that is the side link between robots, cellular network communication, the uplink downlink to the G-Node Bs, and the edge computing, which is the security controller in the cloud. This multi-layered approach allows for efficient real-time data sharing and decision-making. Some of the key technical aspects shown here are real-time collaboration. The system enables real-time information sharing among robots, security staff, and the remote security controller. This allows for quick response to security events and efficient coordination of security resources. Synchronized transmission, as mentioned in the spec, synchronized transmission among participants is crucial. This ensures that data from all robots arrives at the decision maker, that is either the security staff or the controller, simultaneously, allowing for coherent situational awareness. Adaptive leadership is another thing that the system shows that it can adapt its leadership structure based on the complexity of the security task, the intelligence level of the robots, and the quality of communication service. Either a robot, the security staff, or the remote controller can take the lead role. Multimodal sensing. Robots are equipped with various sensors, cameras, potentially thermal imaging, motion sensors, etc., to gather comprehensive environmental data. And scalability. The architecture supports multiple robots and can easily scale to cover larger areas or more complex security scenarios. And it has flexibility in communication. Robots can use direct network connections or indirect network connections, that is via other robots, based on the quality of communication service, enhancing reliability and coverage. The use of multi-access edge computing allows for rapid processing of complex data like video streams close to the source, reducing latency and bandwidth requirements. This diagram effectively illustrates the key components and interactions of the real-time cooperative safety protection system, showcasing how advanced networking and robotics technologies can be integrated to create a sophisticated, adaptive, or adaptable security solution. Here's another diagram quite similar to the previous one. It also illustrates the schematic diagram of data transmission in a safety protection task. It's similar, but there are some differences, so bear with me and let me break down some of the technical details. We have 3 robots, UE1, UE2, and UE3 are shown here, each equipped with sensors and communication capabilities. These robots act as UEs, user equipment, in the 5G network context. We have a human security staff member, which is UE4, present here, equipped with a UE device for communication and data visualization. There are 2 Genobis, which are 5G base stations, are also depicted, providing network coverage and connectivity. That's the network infrastructure. Represented by a cloud icon, there's a representation of an application function running on MEC, multi-access edge computing infrastructure, responsible for processing data and coordinating the security operation. So this is like a security controller. Again, you see the UE, UL, DL, doubling downlink communication links, which connect robots and security staff to Genobis. The SL, which is the side link, provides direct communication between robots. For data transmission visualization, at the bottom of the diagram shows a time-based representation of data transmission from each UE, robot and security staff. So those are the components. Some of the key technical aspects here that I'd like to mention are synchronized data transmission. Each UE, which is UE1, UE2, UE3, and UE4, transmits data in specific time slots. The blue blocks represent successful data transmissions. Purple blocks indicate, it's a slight difference, but you can still tell blue blocks and purple blocks. Purple blocks represent successful data transmissions. Blue blocks represent successful data transmissions. Purple blocks indicate data that couldn't be transmitted on time. Represented by the bracketed area in the transmission visualization is the decision period. This is the time window in which data from all UEs should arrive for processing and decision making. UE3 shows a situation where some data packets, purple blocks, couldn't be transmitted within the allotted time slot. This illustrates the challenge of ensuring synchronized arrival of data from all participants. So that illustrates transmission challenge. As per the specification of 3GPP specification, when some data packets from one UE, for example UE3, can't be transmitted on time, other data packets from other UEs with the same timestamp should be discarded to save network resources. This is the kind of a data processing strategy that is being employed. So this strategy ensures that the decision-making process uses a complete set of synchronized data to make decisions, not partial. The diagram emphasizes the need for real-time data transmission and processing. It's a real-time requirement. The specification mentions that decisions are made every 100 milliseconds, which aligns with the depicted decision period. There are QoS considerations too, of course. Different UEs may experience varying QoS, quality of service, due to their positions or environmental factors. The system must account for these variations to maintain overall performance. The diagram also shows 3 robots and 1 security staff, but the system is designed to scale to larger numbers of participants. So there's a scalability elements here, and it's possible to scale to very large, a large system with a large number of participants. No issue. The security controller in the Mac, in the mobile edge computing data center, processes data close to the source reducing latency and enabling real-time decision making. We talked about adaptive leadership earlier in the previous slide. While not explicitly shown in this diagram, the specification mentions that leadership on decision making can be assigned to a robot, security person, or remote controller based on the situation. We need this level of flexibility. The specification also mentions various data types being transmitted, including location, target characteristics, camera information, and channel state information. So it allows for different data types. The diagram illustrates the challenges of ensuring that data packets from all UEs arrive at the decision maker simultaneously, which is crucial for coherent situational awareness. So in conclusion, this diagram effectively visualizes the complex data transmission patterns in a real-time cooperative safety protection scenario. It highlights the critical aspects of synchronized data delivery, the challenges of maintaining consistent communication in varying conditions, and the importance of efficient data processing strategies. The use of edge computing and advanced networking techniques is crucial to meeting the stringent real-time requirements of such a security system. Use case 3, smart communication for data collection and fusion. This use case explores the intricate process of robots collaborating to build comprehensive information sets through data and sensor fusion. Applications range from underwater sensor networks for marine research to environmental monitoring for climate studies. The system operates on 3 key levels of fusion. 1. Sensor level fusion. Raw data from various sensors, for example, temperature, pressure, chemical composition, is combined to create a more accurate or complete measurement. This often involves statistical techniques like Kalman filtering or particle filters to handle sensor noise and uncertainties. Feature-level fusion. Extracted features or patterns from different data sources are combined. For instance, in environmental monitoring, features like vegetation indices from optical sensors might be fused with soil moisture data from radar sensors. Decision-level fusion. High-level information from multiple sources is combined to make final decisions or predictions. This could involve techniques like Dempster-Sheffer theory or Bayesian inference to handle uncertainties and conflicting information. We're not going to go into the explanations of the Dempster-Sheffer theory or Bayesian inference. We talked about Bayesian inference quite a bit in the previous slides, but you can look them up pretty easily. You have the names here. The system emphasizes energy-efficient and situation-aware communication, crucial for long-term deployments in remote or challenging environments. This involves adaptive sampling. Robots dynamically adjust their sensing and communication rates based on the observed phenomena and available energy resources. Comprehensive sensing. Techniques to reconstruct signals from fewer samples than traditional methods require reducing the amount of data that needs to be transmitted. Event-driven communication. Instead of constant data streaming, robots only transmit when significant changes or events are detected. The system must also dynamically adapt to changing communication needs and opportunities. This could involve cognitive radio technologies or cognitive radio techniques, allowing robots to opportunistically use available spectrum bands, enhancing communication flexibility. Delay-tolerant networking. implementing store and forward mechanisms for scenarios where continuous connectivity isn't guaranteed. Thirdly is multi-hop routing, enabling robots to relay data through multiple hops to reach a destination, extending the effective range of the network. A major challenge is supporting different fusion levels efficiently while adapting to fluctuations in available communication resources. This requires intelligent algorithms to decide what level of fusion to perform locally versus centrally, and how to prioritize data transmission based on its importance and current network conditions. We have a diagram for use case 3. This diagram illustrates examples of using sensor data where objects are in different dimensions or sizes and or in different ranges. The diagram is divided into two scenarios, A and B, each demonstrating a different aspect of sensor data usage in robotic scenarios. Let's take a look at scenario A first. There are two distinct objects, A and B, of the same size that are shown at different distances from the robot. We have a single robot, which is depicted with its intra-robot operation module. So we're doing intra-robot operation here, doing update action/control block. This represents the robot's decision-making and control system. Estimator/input feedback loop. This indicates the robot's ability to estimate object properties and use this information to update its actions. The green fan-shaped area represents the robot's sensing field, likely using the technologies like LiDAR, LiDAR, radar, or computer vision. We have range indicators. The capital letter R denotes the range to object A. The small letter r denotes the range to object B, as in Bob, which is closer to the robot than object A. We have some curved lines. These could represent the sensor's detection boundaries or fields of view for each object. So that's scenario A. Let's take a look at scenario B. There are two distinct objects also, A and C, of different sizes that are shown here in scenario B, approximately the same range from the robot. Similar to scenario A, a single robot with its intra-robot operation module is shown. Intra-robot operation is done here identical to scenario A, demonstrating consistency in the robot's internal processes across different scenarios. The green fan-shaped area again represents the robot's sensing field. Big R, the capital letter R, denotes the range to both object A and object C, illustrating that they are at approximately the same distance from the robot. What are some of the technical details and implications that this diagram is telling us? The diagram implies the use of sensors capable of detecting objects at different ranges and of different sizes, suggesting multimodal or advanced sensing capabilities. The estimator/input feedback loop in the intra-robot operation module indicates that the robot is performing some level of data fusion, combining sensor data to estimate object properties and locations. The robot's ability to detect objects of different sizes at various ranges suggests an adaptive sensing system capable of adjusting its parameters based on the environment. So adaptive sensing capability is implied here as well. The update and control mechanism implies real-time processing of sensor data to make immediate decisions and actions. Although one robot is shown on this diagram, the use case in the specification discusses multiple robot scenarios or multi-robot scenarios, suggesting that this sensing and processing model is scalable to multiple robots working collaboratively. Scalability is being considered. It's totally scalable. While not explicitly shown, the specification discusses the need for efficient communication to share this sensor data among robots or with edge computing resources. The diagram also refers or relates to the discussion in the specification about different levels of data fusion. That is sensor level, feature level, decision level. The intra-robot operation module likely implements one or more of these fusion levels. So there is supporting different levels of fusion. The specification, well, when I say the specification, that implies a 3GPP specification. The specification emphasizes the importance of energy efficient and resource efficient operation. The compact representation of the intra-robot operation module suggests an optimized, efficient processing system. So the system has to be designed in a resource efficiency manner. The robot's ability to differentiate between objects of different sizes and at different ranges implies a sophisticated contextual understanding of its environment, which is crucial for many of the use cases described in the specification. So contextual decision-making is a requirement. To conclude, this diagram effectively illustrates the challenges and capabilities of robotic sensing systems in complex environments, highlighting the need for advanced sensing, processing, and decision-making capabilities in multi-robot systems. It underscores the importance of efficient data handling and fusion techniques, which are key themes in this particular use case. This is another diagram for use case 3. This diagram illustrates an example of different levels of communications opportunity need or transmission opportunity need under a combination of normal and challenging or extreme communication conditions. Let's break down the technical details of depicted on this diagram. The diagram shows 6 robots represented by small humanoid figures with camera-like heads. These robots are positioned both inside and outside a designated area, represented by a rectangle. So this is showing us the robot configuration essentially. Each robot has a blue cone extending from its head, so-called head, representing its sensing range. This could be visual, LiDAR, or other types of sensors. So it is showing us the sensing capabilities. 2 types of communication links are shown, a green zigzag line representing normal coverage or normal range. There's an orange zigzag line or lines representing extended coverage or extended range. These are the two types of communication links, orange zigzag lines or green zigzag lines. So under the normal coverage or range, these are shown by green lines connecting robots outside the rectangle to these or to those out inside. These represent standard communication links under normal conditions. For extended coverage or extended range, these are shown by orange lines connecting robots within the rectangle. These represent communication links under challenging or extreme conditions requiring extended range capabilities. So Just in real life, we have dynamic environment. Our environment is always dynamic if it's not entirely controlled. So this diagram illustrates a dynamic environment where communication needs and capabilities can change based on the robot's positions and environmental conditions. The rectangle in the center is labeled reliable support of dynamic transmission opportunity negotiation, quote unquote. This suggests an area where more advanced or adaptive communication strategies are employed. I want to talk about some of the technical implications and details regarding this diagram. The system must adapt to different communication needs based on the robot's positions and environmental conditions. This aligns with the specification's emphasis on smart cooperation and efficient use of communication resources. So adaptive communication is a requirement and should be designed into this kind of systems. The different communication ranges, that is normal and extended, suggest the need for multi-level data fusion as described in the specification. Robots may need to process and fuse data differently based on the quality and type of communication links available. So we must support multi-level fusion. The quote-unquote reliable support of dynamic transmission opportunity negotiation implies that the system can dynamically allocate communication resources based on current needs and conditions. This is crucial for efficient operation in changing environments. That is, we need to support dynamic resource allocation. The diagram shows multiple robots working together, illustrating the scalability of the system as described in the use case. It can scale from one robot to hundreds of robots. The combination of normal and extended coverage suggests a heterogeneous network architecture capable of handling different types of communication links and ranges. QoS management is another aspect that needs to be considered carefully. The system must manage QoS, quality of service, across different communication scenarios, ensuring critical data is transmitted even in challenging conditions. So QoS is not considered only on one platform or one communication scenarios, but across different communication scenarios. That is a challenge. The distinction between normal and extended coverage implies different energy requirements for communication. This relates to specifications focus on energy-efficient operation. Energy efficiency is a must in this kind of designs. Next is context awareness. Robots must be aware of their environment and communication capabilities to choose the most appropriate communication strategy. Context awareness is a must. And we need to support collaborative sensing. The overlapping sensing cones suggest that robots can collaborate to build a more comprehensive understanding of their environment, as described in the use case for collaborative 3D mapping. The different sensing ranges imply that robots can adjust their sensing capabilities based on their current role and position within the network. So adaptive sensing, of course, is part of the consideration. Real-time adaptation refers to the dynamic transmission opportunity negotiation, suggests that the system can make real-time decisions about how to allocate communication resources, a crucial feature for the real-time cooperative scenarios described in the specification. And resilience is a consideration. The ability to maintain communication in both normal and extended coverage scenarios indicates a resilient system design, capable of maintaining operation under varying conditions. This diagram effectively illustrates the complex and dynamic nature of communication in multi-robot systems, highlighting the need for adaptive, efficient, and resilient communication strategies. This includes smart cooperation, efficient resource usage, and the ability to operate in challenging and changing environment. I want to note here that a lot of these key points are going to be repeated in the different use cases. So you'll be hearing a few of the same ideas, same key points over and over in these different use cases. The reason of doing this and doing this repetitiveness is that anybody can jump through the different use cases and focus on each one of them and hear the whole story. So that's the purpose of repeating some of these. And I think if you hear them enough, it will become very intuitive, and you can even recite them out yourselves when talking about these different use cases. So please bear with me with this repetitiveness, and there is a reason to it. So, all right, let's move forward. This is also another diagram that belongs to use case 3. This diagram illustrates examples of underwater sensor network applications. It represents a hierarchical structure of various applications for underwater sensor networks, UWSN in short, underwater sensor networks. Let me break it down a little bit for you, what we're looking at. We are looking at main categories of UWSN applications. Again, UWSN is underwater sensor networks. What are the main categories? Monitoring, disaster, military, assisted navigation, and sports. Monitoring applications, under monitoring applications, we have water quality, habitat, and under habitat, we have marine life, fish farms, and reef. Exploration is another monitoring application, and underneath it, we have natural resources, pipeline, and cables. Disaster applications including flood, volcano, earthquake, and tsunami. Oil spill also. For military applications, we have mines, submarines, and surveillance. What are some of the technical implications and details? Diverse application scope. You are looking at a diagram that showcases a wide range of applications for UWSNs, spanning from environmental monitoring to military operations. This diversity implies the need for flexible and adaptable sensor network architectures. We are also looking at multi-level sensing requirements. Different applications require various types of sensors and data collection methods. For example, water quality monitoring might need chemical sensors, while submarine detection could require acoustic sensors. They're very different. Different applications, different requirements. And we have data fusion challenges. As mentioned in the specification, these diverse applications would require different levels of data fusion. For instance, disaster monitoring might need real-time data fusion from multiple sensor types, while habitat monitoring could involve long-term data collection and analysis. There are communication challenges. Underwater environments pose unique challenges for communication. The specification mentions the need for efficient and reliable communication in various scenarios, which is particularly crucial for underwater applications due to limited bandwidth and high latency in water. Many of these applications, especially long-term monitoring ones, would require energy-efficient operation of sensors and communication systems, aligning with the specification's emphasis on energy efficiency. What about real-time versus delayed communication? Some applications, for example, tsunami detection, would require real-time data transmission, while others, for example, reef monitoring, might allow for delayed data collection. This variety aligns with the specification's discussion on different levels of communication needs. The broad range of applications suggests the need for scalable sensor network architectures, capable of supporting both small scale, for example, sports applications, and large scale, for example, ocean exploration deployments. Interoperability is very important. Given the diverse set of applications, there's an implicit need for interoperability between different types of sensors and communication systems, which relates to the specification's focus on efficient cooperation among multiple robots or sensors. Applications like flood or tsunami monitoring imply the need for sensors that can adapt to rapidly changing environmental conditions, reflecting the specification's emphasis on adaptability in challenging environments. Many applications, especially military applications, highlight the need for secure communication and data protection, which, although not explicitly mentioned in this section of the application, of this specification, pardon me, is a crucial aspect of sensor network deployments. So like in every system, security and privacy has to be one of the main concerns regarding design and implementation. The quote-unquote assisted navigation category implies the need for accurate underwater localization technologies, which can be challenging due to limitations of GPS underwater. Some applications like oil spill monitoring would require integration of underwater sensors with above water or land-based systems, suggesting the need for seamless communication across different domains. So multi-domain integration is part of the concern in terms of design and implementation. So to conclude, this diagram effectively illustrates the complexity and diversity of underwater sensor network applications, underlying the need for advanced sensing, communication, and data processing capabilities. It aligns well with the specification's focus on smart cooperation, efficient resource use, and adaptability in challenging environments, while also highlighting the potential for robotic applications in underwater scenarios. The variety of applications presented here reinforces the importance of flexible and efficient communication strategies as discussed in this use case. Here's another diagram for use case 3. This diagram illustrates the underwater sensor network architecture in a more precise manner. The image provides a comprehensive view of how underwater sensor networks are structured and how they communicate with terrestrial systems. So let's break down the different components a little bit and also look at the technical details. What are the network components? We have underwater devices or nodes, underwater nodes. Those are the yellow circular icons. We have AUV. AUV stands for Autonomous Underwater Vehicle. Those are submarine-like icon that you can see here. It's just a little bit busy. I hope you can identify what I'm talking about. We also see service stations like those buoys and boats. For the terrestrial communication infrastructure, you can see satellite and onshore infrastructure represented by the various icons. What are the communication types we're seeing here? 1D underwater communication, those are the linear arrangement of nodes. 2D underwater communication, planar arrangement of nodes. 3D underwater communication, those are the volumetric arrangement of nodes. Last but not least is the 4D underwater communication. Those are the dynamic 3D arrangement with mobile nodes, for example, AUVs, autonomous underwater vehicles. So those are the 4 different communication types. In terms of network structure, we have offshore underwater network that are divided into clusters. We have service network. Those are the buoys, buoys and boats. I couldn't quite pronounce that word most of the time. Buoys and boats acting as gateways. And we have terrestrial network. Those are the onshore infrastructure and satellite. For wireless links, they are represented by wavy lines connecting various components. All right, the technical details regarding this picture. This is we're looking at a multi-layered architecture. The system employs a multi-layered approach from underwater sensors to service stations to terrestrial infrastructure. This aligns with the specifications discussion on multi-level data fusion and communication needs. We are looking also at a cluster-based deployment. Underwater nodes are organized into clusters. We have cluster 1 and we have cluster 2, which can enhance energy efficiency and facilitate local data processing, as emphasized in the specification. The system uses different communication methods. As we mentioned earlier, we have 1D, 2D, 3D, and 4D communication methods based on the deployment scenario, showcasing the adaptability required in challenging underwater environments. The presence of AUVs, autonomous underwater vehicles, indicates mobile sensing and communication capabilities, which can dynamically adjust the network topology and collect data from hard-to-reach places or hard-to-reach areas. Buoys and boats act as gateways between the underwater network and terrestrial systems, addressing the challenge of transitioning between aquatic and air-based communication. So these are the so-called service to underwater gateway. The architecture supports a scalable deployment from simple 1D communication to complex 4D scenarios, aligning with the specification's emphasis on scalable and efficient use of communication resources. The clustered structure implies multi-hop communication among underwater nodes, which is crucial for energy efficiency in large-scale deployments. The connection to terrestrial infrastructure suggests the capability for real-time data transmission to onshore facilities, supporting applications that require immediate data analysis and response. The varied deployment depths and communication types demonstrate the system's adaptability to different underwater environments, a key aspect highlighted in the specification. And of course, we have energy efficiency considerations. The clustered approach and use of service gateways can help optimize energy usage in underwater nodes, addressing the energy efficiency concerns mentioned in the specification. The architecture supports both sensing through underwater nodes and AUVs and communication, enabling the smart cooperation scenarios described in the specification. The system allows for data fusion across underwater, surface, and terrestrial domains, supporting complex applications that require integrated data from multiple sources. There are localization challenges. The 3D and 4D communication scenarios imply sophisticated localization techniques for underwater nodes, addressing the challenges of positioning in aquatic environments. There are temporal aspects to this design. The inclusion of 4D communication suggests consideration of temporal aspects in data collection and network management, aligning with the dynamic nature of underwater environments. The multi-layered approach with multiple service stations provides redundancy, enhancing the overall resilience of the network. So again, to conclude, this diagram effectively illustrates the complexity and versatility of underwater sensor network architectures. It aligns closely with the themes discussed in this use case, particularly in terms of adaptive communication strategies, efficient resource usage, and the ability to cooperate in challenging environments. The architecture's support for various communication types and its integration of mobile elements, the AUVs, demonstrate the potential for sophisticated robotic applications in underwater scenarios. As envisioned in the specification's use cases for smart cooperation and data fusion in multi-robot, multi-agent scenarios. Okay, now use case 4. Media-related applications. This use case focuses on the application of surface robots in media-rich scenarios, particularly video surveillance for indoor environments and intelligent transportation systems. These applications leverage advanced computer vision and machine learning techniques to extract and communicate relevant information efficiently. Key features of the system include object detection and tracking, utilizing state-of-the-art deep learning models like YOLO, which is you only look once. YOLO, that's the acronym of it. You only look once. We've talked about YOLO for quite some time in the previous slide deck. Or faster RCNN for real-time object detection. For tracking, algorithms like SORT, which is short for Simple Online and Real-Time Tracking, or Deep Sort, are employed to maintain object identities across frames. Feature extraction and sharing. Instead of transmitting full video streams, the system extracts relevant features, for example, object bounding boxes, pose estimations, activity classifications, etc., and shares these compact representations. This significantly reduces bandwidth requirements. Optimized bandwidth usage for machine interpretation. The system employs novel video coding techniques optimized for machine consumption rather than human viewing. This could involve semantic video compression methods that prioritize preserving information critical for AI analysis over perceptual quality. In the context of indoor video surveillance, the system might use depth sensors in addition to RGB cameras to create 3D representations of the environment. This allows for more accurate object localization and improved handling of occlusions. For intelligent transportation systems, the robots could be mobile platforms equipped with multiple sensors, for example, cameras, LiDAR, or radar, to monitor traffic flow, detect anomalies, and even interact with a smart infrastructure. The primary challenges in this use case revolve around efficient conveyance of media signals for machine-type communications. For example, low latency encoding. Developing ultra-fast encoding algorithms that can compress video in real time without introducing significant delays. Content-aware compression. Implementing intelligent compression schemes that adapt based on the scene content and the specific requirements of downstream AI tasks. Distributed processing. Leveraging edge computing to perform initial processing and feature extraction on the robots themselves, reducing the amount of data that needs to be transmitted over the network. Scalable video coding. Implementing layered coding schemes that allow for progressive refinement of video quality based on available bandwidth and the requirements of the current task. So, by addressing these challenges, the system aims to achieve significantly improved compression efficiency compared to traditional codecs designed for human consumption, while maintaining or even enhancing the performance of machine vision tasks. This diagram illustrates the use case on video surveillance. The image provides a comprehensive view of a video surveillance system architecture. So what are we looking at here? We're looking at a few system components, which include front end, that is a surveillance, that are surveillance cameras and front end devices. We have the back end, which is essentially the cloud server, and the human element, which is the supervisor. For the front end, I want to talk a bit more about it. Multiple surveillance cameras are depicted, suggesting a distributed surveillance network. A front-end device, shown as a small black box, is included, which likely serves as a local processing unit or gateway. On the back end, a cloud server is represented, indicating centralized data storage and processing capabilities. For this human supervisor, there's a human supervisor included in the system, highlighting the role of human oversight in the surveillance process. Arrows between the front end and back end represent data transmission paths. These are communication links that we're talking about next. A link between the human supervisor and the cloud server suggests a monitoring or control interface. What are the technical details and their implications? We are using here, or what's shown here, illustrating a distributed sensing network. The multiple cameras in the front end, aligned with the specifications, focus on multi-robot or multi-agent scenarios where multiple devices collaborate to gather comprehensive data. The presence of front-end devices suggests local processing capabilities, which can support the feature extraction mentioned in the specification. This aligns with the goal of optimizing uplink bandwidth usage using edge computing. The cloud server in the back end enables centralized data analysis and storage, supporting sophisticated processing tasks like object detection and tracking mentioned in the specification. The direct links between front-end devices and the cloud server imply real-time or near real-time data transmission, critical for timely event detection and response. We have human in the loop. The inclusion of a human supervisor aligns with the specifications mention of scenarios where human understandability is not required, but human oversight is still maintained. The architecture supports multiple cameras and devices, indicating scalability to cover large or complex environments. As mentioned in the specification, this architecture allows for optimized use of uplink bandwidth. Front-end processing can extract relevant features or compress data before transmission to the cloud. The specification emphasizes that image quality requirements are limited to machine interpretation. This architecture supports this by potentially processing and transmitting only the necessary data for automated analysis. The front-end devices and cloud server can collaboratively perform tasks like feature extraction, object detection, and tracking, as highlighted in the specification. The separation of front-end and back-end components allows for flexible deployment in various environments, supporting different surveillance scenarios mentioned in the specification. For example, intrusion detection, fire detection, etc. The cloud server can perform data fusion from multiple cameras and sensors, enabling comprehensive situation awareness and event detection. So that's the data fusion part of the equation. The architecture allows for adaptive processing strategies. For example, the front-end devices could adjust their processing based on detected events or instructions from the cloud server. Adaptive processing is totally part of this equation. While not explicitly shown, the centralized architecture implies the need for robust security measures to protect sensitive surveillance data. The specification mentions the importance of standardized compact bit streams for interoperability. This architecture would support such standardized communication between the front end and back end. To conclude, this diagram effectively illustrates a video surveillance system that aligns with the key points discussed in this use case. We're still in use case 4, of course. It supports the goals of efficient bandwidth usage, feature extraction, and machine-focused processing while maintaining human oversight. The architecture's flexibility and scalability make it suitable for various surveillance applications, from intrusion detection to complex event recognition, as envisioned in the specification's use cases for media-related robotic applications. This diagram illustrates the use case on V2X, vehicle-to-everything communications. The image provides a detailed view of V2X communication in an intelligent transportation scenario. Let me break down the technical details. System components on this diagram, we have a few of them. Vehicles, that we have 2 cars equipped with multiple sensors and communication devices. We have cellular infrastructure, which is like a cell tower icon for network connectivity. We have roadside units. They're depicted as gray squares, likely for short-range communication. Visual processing, shown as image insets representing different types of visual data. On the equipment, on the vehicle, their equipment, multiple small squares on the vehicles represent various sensors, for example, cameras, LiDAR, radar, etc. A blue box inside each vehicle likely represents the onboard processing unit or V2X communication module. Blue dashed line between vehicles, those are direct V2V, vehicle-to-vehicle communication links. We have the gray dashed lines. Those are V2I, vehicle-to-infrastructure communication links with a cell tower and roadside units. Each vehicle is associated with 2 images. A processed image showing object detection and classification, for example, road markings or other vehicles. A raw camera feed of the road scene. Those are visual processing outputs. So next, I'd like to take a look at what are some of the technical details of what they entail and what are the implications. The vehicles are equipped with multiple sensors, aligning with the specification's focus on using various data sources for comprehensive environmental understanding. So that's multimodal sensing. The presence of onboard processing units, the blue boxes, suggests real-time data processing and feature extraction, as mentioned in the specification. Those are for real-time processing. The direct link between vehicles enables the sharing of processed data or extracted features, supporting the specification's emphasis on efficient bandwidth usage. Those are V2V communication, vehicle-to-vehicle communication. For V2I communication, vehicle-to-infrastructure, those are connections from the vehicle to infrastructure, cell tower and roadside units. Those connections allow for broader data sharing and access to cloud resources, enhancing the overall system's capabilities. The processed images indicate local feature extraction and object recognition, which can be compressed and transmitted more efficiently than raw video data, as highlighted in the specification. By processing data locally, and transmitting only relevant features or compressed information, the system optimizes bandwidth usage, a key point in the specification. That's bandwidth optimization. The processed images demonstrate machine-centric video analysis, focusing on extracting relevant information for autonomous driving rather than human viewing, making full use of machine-centric video analysis. The architecture shows a distributed intelligence approach, with processing occurring both in vehicles and potentially in infrastructure, supporting scalable and efficient operation. So this is the kind of distributed intelligence we are talking about. The combination of multiple sensors and processed visual data enables comprehensive environmental awareness, crucial for intelligent transportation systems. That is, to have environmental awareness. While not explicitly shown here, the V2V and V2I communications imply the use of standardized data formats for interoperability, as mentioned in the specification. The direct V2V, vehicle-to-vehicle link, suggests low-latency communication for time-critical information sharing between vehicles. The architecture can scale to include more vehicles and infrastructure elements supporting complex traffic scenarios. The onboard units can potentially adapt their processing and communication strategies based on current traffic situation and available bandwidth. That is the adaptive processing capability that it requires. The multiple sensors on each vehicle enable sensor fusion techniques, combining data from various sources for more accurate environmental understanding. That's the sensor fusion capability. The roadside units could serve as edge computing nodes, providing additional processing power and low latency services to vehicles. This diagram effectively illustrates a V2X communication system that aligns closely with the key points discussed on the 3GPP specification. It demonstrates how vehicles can act as mobile sensor platforms, processing and sharing relevant data efficiently. The architecture supports the goals of bandwidth optimization, feature extraction, and machine-focused processing while enabling complex intelligent transportation scenarios. This use case showcases the potential for sophisticated robotic applications in vehicular environments, emphasizing the importance of efficient communication and data processing strategies in dynamic, safety-critical situations. We're on to use case 5, smart community. This use case explores the integration of service robots in continuing care retirement communities, CCRC for short, continuing care retirement communities, showcasing how robotics can enhance quality of life and safety in specialized residential settings. The system incorporates various types of robots, each designed for specific tasks. Patrol robots for crime prevention and safety. These robots, equipped with advanced surveillance cameras, thermal imaging, and potentially LiDAR for 3D mapping, utilize AI-driven anomaly detection algorithms to identify unusual activities or potential security threats. Capable of autonomous navigation using SLAM, remember SLAM? Simultaneous localization and mapping techniques. And we have natural language and gesture recognition robots for smart home control. These robots implement advanced natural language processing (NLP) models, possibly based on transformer architectures like BERT or GPT, for understanding complex voice commands. They use computer vision techniques for gesture recognition, allowing for intuitive control of smart home devices. It also integrates with IoT, Internet of Things platforms to interact with various smart devices in the home. Next, we have delivery robots for groceries and parcels. These robots employ path planning algorithms for efficient navigation through the community, use computer vision for obstacle detection and avoidance, implement secure authentication mechanisms for package delivery and retrieval. Some of the key features of this system include seamless indoor-outdoor operation. The robots must transition smoothly between indoor and outdoor environments, adapting to different navigation challenges and communication infrastructures. This might involve hybrid localization systems that combine GPS, Wi-Fi positioning, and visual odometry. Integration with existing infrastructure. The robotic system needs to interface with various smart devices and systems already present in the community. This requires implementing standardized communication protocols, for example, MQTT, COAP, and possibly developing middleware for legacy system integration. Privacy-conscious local data processing, that is to address privacy concerns, especially in a residential setting. The system employs edge computing techniques to process sensitive data locally on the robots or on local edge servers. This minimizes the amount of personal information transmitted over the network. The primary challenges in implementing the system include maintaining service continuity. As robots move between different areas, indoor, outdoor, different buildings, they need to seamlessly transition between various network conditions. Wi-Fi, cellular, potentially satellite in some areas. This requires implementing robust handover mechanisms and possibly multi-homing capabilities. Balancing privacy with data sharing. While local processing helps with privacy, some level of data sharing is necessary for efficient operations. The system must implement strong encryption, access control mechanisms, and data minimization techniques to protect resident privacy while still allowing for effective robot coordination and service delivery. Human-robot interaction in a retirement community setting needs to ensure intuitive and accessible interaction between residents and robots, and that's quite crucial to have it done right. This might involve developing multimodal interaction systems that combine voice, gesture, and touch interfaces, with a focus on accessibility for users with varying physical and cognitive abilities. There are regulatory compliance to be considered. Operating in a healthcare adjacent environment means adhering to strict regulations. For example, HIPAA in the US. The system must be designed with these compliance requirements in mind, particularly in terms of data handling and storage. By addressing these challenges, the smart community system aims to create a safe, efficient, and comfortable living environment that leverages the unique capabilities of service robots while respecting the privacy and autonomy of residents. Here we have a simple diagram, quite simple. Diagram illustrates patrol robots in the CCRC. Again, CCRC stands for Continuing Care Retirement Community. Let's break down the technical details and implications. Regarding the environment, we have the oval shapes representing the CCRC, that's gray color areas, and the cellular coverage area, that is yellow shaded. There are multiple houses or buildings are shown here within the CCRC, indicating a residential community setting. The different types of robots that would be servicing this kind of smart community are ground-based patrol robots, depicted as small humanoid figures here. We have aerial patrol robots, drones, shown as quadcopter icons. We have stationary surveillance cameras represented by camera icons. So we have these three different types of robots. Oh, and two different types of robots and the stationary surveillance cameras. In terms of cellular coverage, the yellow area indicates cellular network coverage, which doesn't entirely cover the CCRC. This partial coverage is a key point addressed in the specification. The use of both ground and aerial robots aligns with the specification's description of a multi-robot system for comprehensive surveillance and assistance. So this is what we call the heterogeneous robot deployment. We have some coverage challenges. The mismatch between the CCRC area and the cellular coverage highlights the need for alternative communication strategies, as mentioned in the specification. While not explicitly shown, the specification mentions the use of stationary relays, possibly the surveillance cameras, to extend network coverage. That is to provide relay functionality. Robots must switch between direct and indirect network connections based on their location within the CCRC as described in the use case. So we need adaptive connectivity. We also need multipath communication. The specification mentions that patrol robots can establish multiple indirect network connection paths when sending surveillance video, which this layout would necessitate. The diverse deployment of robots and sensors demonstrates the scalability of the system to cover large areas with varied terrain. Terrain. Pardon me. The system must manage the mobility of patrol robots as they move through areas of varying network coverage. As robots move around the community, maintaining service continuity is crucial, especially for tasks like tracking potential security threats. The specification mentions robots responding to security events or medical emergencies, which this layout supports through comprehensive coverage. So here we are referring to event-driven operation. The combination of ground robots, aerial drones, and stationary cameras enables multimodal data fusion for enhanced situational awareness. The extensive coverage of residential areas implies the need for robust privacy protection measures. While not directly shown, the specification emphasizes the need for energy-efficient operation, particularly important for mobile robots patrolling large areas. The system likely employs a hierarchical control structure with a central monitoring station coordinating the various robots and cameras. Robots and drones can adapt their sensing and patrolling strategies based on the specific needs of different areas within the CCRC. The layout supports quick response to medical emergencies, with robots capable of reaching residents rapidly and connect with their personal smart devices. The specification mentions robots getting temporary authorization to connect to residents' devices in emergencies, a feature supported by this comprehensive coverage. For medical events, the system supports synchronized transmission of vital signs and live video, requiring coordinated communication among multiple devices. So synchronized communication is called for. This diagram effectively illustrates the complex and comprehensive nature of the patrol robot system in a CCRC situation. It highlights the challenges of ensuring consistent communication coverage in a large residential area and demonstrates the potential for a multi-robot system to provide enhanced security and medical assistance. The layout emphasizes the need for adaptive communication strategies, efficient resource management, and seamless integration of various robotic and sensing elements to create a robust and responsive care environment for residents. All right, this diagram is very similar to the previous one. This diagram illustrates a medical assistance event with patrol robots. So it's very similar to the previous diagram. I'm going to quickly go through them because in case you are looking at specific use cases on an individual basis, I want this to be a whole story rather than a partial one. So in terms of the environment, we have the oval shape representing the continuing care retirement community, CCRC in short. We have multiple houses or buildings that are shown here within the CCRC, indicating a residential setting. Again, we have this time we have 4 different types of robots and devices. We have the ground-based patrol robots depicted as humanoid figures, one highlighted in blue. We have the aerial patrol robots, those are drones, shown as quadcopter icons. We have stationary surveillance cameras represented by camera icons. Lastly, we have medical assistance robot, the blue humanoid figure likely equipped with medical capabilities. So in an event, a medical assistance event, an arrow points from the blue robot to a specific house, indicating a medical assistance event is in progress. So what are some of the technical details and implications? This requires or indicating that an event-driven response is in progress. The diagram shows a medical assistance robot actively responding to an event, aligning with the specification's description of event-driven operation. The presence of various robots, ground, aerial, and specialized medical robots, demonstrates the system's ability to coordinate multiple units for a single event. The direct path of the medical robot to the affected house illustrates the system's capability for quick response to medical emergencies. So this is a rapid response incident. The distribution of robots and cameras throughout the CCRC ensures full coverage for detecting and responding to emergencies, like this one. While not explicitly shown, the specification mentions synchronized transmission of vital signs and live video during medical events. This would require robust real-time communication capabilities among the robots and infrastructure. The specification notes that robots may receive temporary authorization to connect to residents' smart devices during emergencies. This capability is implied in the medical robot's interaction with the target house. The combination of stationary cameras, aerial drones, and ground robots allows for multimodal data fusion, providing comprehensive situational awareness during the medical event. The medical robot's direct path suggests an adaptive routing capability, allowing it to navigate efficiently to the emergency location. The system must balance comprehensive surveillance with resident privacy, especially during sensitive medical events. As the medical robot moves through the community, it may need to switch between different network access points, requiring seamless communication handover. So seamless handover is absolutely required. During a medical event, the system likely prioritizes communication resources for the responding medical robot to ensure uninterrupted data transmission. The layout here demonstrates the system's capability or scalability, capable of handling multiple simultaneous events across a large residential area if needed. While not shown, the specification implies that the medical robot can interact with residents, possibly through voice commands or a user interface. So human-robot interaction requires some sophisticated design to make it really easy and simple. Environmental awareness refers to the various robots and sensors provide environmental context, potentially alerting the medical robot to obstacles or optimal paths. For prolonged medical events, the system must manage energy efficiently, especially for battery-powered mobile robots. While not visible, the system likely incorporates redundancy and fail-safe mechanisms to ensure continuous operation during critical medical events. The medical response system may integrate with external emergency services, though this is not explicitly shown in this particular diagram. This diagram effectively illustrates the medical assistance capabilities of the patrol robot system in a CCRC situation. It highlights the system's ability to quickly identify and respond to medical emergencies, leveraging a network of diverse robots and sensors. The layout emphasizes the importance of coordinated action, rapid response, and seamless communication in providing effective medical assistance to CCRC residents. This use case demonstrates how advanced robotic and communication technologies can significantly enhance the safety and care provided in retirement communities. Use case 6. Real-time conversational robot. This use case focuses on the development and deployment of advanced voice bots capable of engaging in natural, real-time spoken conversations, with a particular emphasis on assisting elderly individuals. The system operates in 3 primary modes, each with its own technical challenges and requirements. Text-based processing, ASR to NLP to TTS. ASR stands for Automatic Speech Recognition, which utilizes deep learning models like deep speech or wave-to-vec, WAV2-VEC, for robust speech-to-text conversion. Natural language processing, NLP, employs advanced language models, for example, BERT, BERT, and GPT, for understanding context, intent, and generating appropriate responses. Text-to-speech, TTS, uses neuro-TTS models like Tachytron or WaveNet for natural-sounding speech synthesis. Audio sample processing, speech to NLP to TTS. This is direct speech processing without intermediate text representation. Uses end-to-end speech processing models that can extract meaning directly from audio features. Potential for lower latency compared to text-based processing. And then we have direct voice call interpretation and response. Real-time processing of voice calls, potentially integrating with existing telephony systems. It requires extremely low latency processing to maintain natural conversation flow. And it may involve adaptive noise cancellation and speaker separation techniques for handling real-world audio conditions. Key requirements for this system include low latency speech processing, implement streaming inference techniques to begin processing speech before the user has finished speaking. It utilizes edge computing to perform initial processing locally, reducing network-induced latencies. Optimize model architectures for real-time performance, potentially using techniques like knowledge distillation or quantization. Natural conversation experience. Develop context-aware dialogue management systems that can maintain coherent conversations over multiple turns. Implement emotion recognition from speech to allow for more empathetic responses. Use reinforcement learning techniques to continuously improve conversation quality based on user interactions. Resilient voice connection with sufficient quality. exploit adaptive bit rate algorithms to maintain call quality under varying network conditions, implement packet loss concealment techniques to handle network disruptions gracefully, use voice activity detection to optimize bandwidth usage during silences. There are some additional considerations for this use case, particularly in the context of elderly assistance, and these include personalization. The system should adapt to individual users' speech patterns, preferences, and needs over time. This might involve creating personalized acoustic and language models for each user. Multimodal interaction. While primarily voice-based, the system could integrate visual cues, for example, displaying information on a screen to aid comprehension, especially for users with hearing impairments. Health monitoring. The conversational system could be extended to monitor the user's well-being through voice analysis, detecting changes in speech patterns that might indicate health issues. Privacy and security. Implement strong encryption for all voice data with clear policies on data retention and usage. Provide easy-to-use controls for users to manage their privacy settings. Fallback mechanisms. Design the system to gracefully handle situations where it cannot understand or assist the user, potentially routing to human operators where necessary. This is especially important to have because when we are dealing with human life or human health, redundancy is required. By addressing these technical challenges and considerations, the real-time conversational robot aims to provide a natural, helpful, and comforting presence for elderly users, enhancing their daily lives and potentially improving their access to information and services. We have a diagram here that is explaining use case 6. We're still on real-time conversational robot. Now, this diagram illustrates the determination of the effects of absolute delay by the E model. The E model is a computational model for assessing the quality of voice transmission, as standardized by ITU-T recommendation G.114. Let's break down the technical details. We have the x-axis, mouth-to-ear delay in milliseconds, ranging from 0 to 600 milliseconds. On the y-axis, we have the E model rating R, ranging from 50 to 100. Let's take a look at the color-coded regions. The red portion, nearly all users dissatisfied, so the R value is less than 60. Pink region indicates many users dissatisfied. 60 R is greater than or equal to 60 but less than 70. On the yellow portion indicates some users dissatisfied. The R value is greater or equal to 70 but less than 80. On the light green portion, it indicates users satisfied. The R value is greater or equal to 80 but less than 90. Dark green indicates very satisfied. The users are very satisfied, and the R value is greater or equal to 90. The curve shows a nonlinear relationship between delay and user satisfaction. It remains relatively flat up to about 150 milliseconds, then declines more rapidly. That's the curve characteristics. So what are some of the implications here? The diagram shows that user satisfaction is relatively insensitive to delays up to about 150 milliseconds. Beyond 150 milliseconds, user satisfaction declines more rapidly with increasing delay. So that shows the delay sensitivity. Around 300 milliseconds delay, the satisfaction the satisfaction level drops from users satisfied to some users dissatisfied. At approximately 500 milliseconds, it reaches the many users dissatisfied level. So those are the two critical thresholds that the diagram is showing. Regarding QoE, QoE stands for quality of experience. The E model rating R directly correlates with user perception of voice quality. Higher R values indicate better perceived quality. In the context of the specification regarding real-time conversational robot, this model can be applied to assess the quality of voice communication between robots or between robots and humans. For applications requiring high user satisfaction, that is R value greater than 80, the system should aim to keep mouth-to-ear delays below 200 milliseconds. So this is a real-time communication requirement. This model can guide the design of communication systems for robots, helping to set appropriate delay targets for different use cases. Network architects can use this model to determine acceptable latency budgets for different parts of the communication system when they're doing network planning. Robotic systems could potentially use this model to dynamically adjust their communication strategies based on current delay conditions. So for adaptive systems, they could use some of these very easy numbers to guide them to see how they could adjust and make their system be more adaptive to the application, whatever their application requires. The model helps in setting realistic expectations for voice quality in different delay scenarios. So this is how you would manage user expectation. The E model rating R can serve as a key performance indicator for voice communication quality in robotic systems. So this is one of the performance metrics that you can use. Using standardized models like this ensures consistency in quality assessment across different robotic platforms and communication systems so that interoperability can be achieved. While not explicitly shown, the mouth-to-ear delay includes various components such as encoding, transmission, and decoding delays. This model is particularly relevant for scenarios where robots interact verbally with humans, as described in the conversational robot use case here in use case 6. So this is sort of an applicability to robot to human interaction. The model focuses on delayed effects and doesn't account for other factors that might affect voice quality in robotic applications, such as background noise or voice synthesis quality. So there are limitations that you need to care about. As mentioned earlier, background noise or voice synthesis quality, or any other areas that you may discover while you are developing your application. This diagram effectively illustrates the relationship between communication delay and user satisfaction in voice transmission, which is crucial for the real-time conversational robot scenarios. It provides a quantitative basis for assessing and designing voice communication systems in robotic applications, emphasizing the importance of minimizing delays to ensure high-quality interactions between robots and humans or among robots themselves. Next use case 7, is about MEC, mobile edge computing, for geosurface sensing with aerial robots. This use case explores the application of aerial robots, drones in other words, aerial robots are mostly, we call them drones, for geosurface sensing tasks, leveraging multi-axis edge computing, MEC, to enhance performance and efficiency. The system has wide-ranging applications in agriculture, wildlife preservation, and urban planning, each with unique requirements and challenges. Let's take a look at some of the key features of this system. They include MEC, multi-access edge computing for enhanced performance. Deploys edge computing nodes in proximity to the operation area, reducing latency and enabling real-time data processing. Implements dynamic task offloading algorithms to balance processing between drones and edge nodes based on current computational loads and network conditions. Utilizes containerization techniques, for example, Docker, Kubernetes, for flexible and scalable deployment of processing applications on edge nodes. Real-time data processing and sharing. Employs stream processing frameworks, for example, Apache Flink, Spark Streaming, for continuous analysis of sensor data. Implements distributed databases, for example, Apache Cassandra, CockroachDB for scalable storage, and quick retrieval of processed data. Uses publish, subscribe, PubSub, messaging systems, for example, Apache Kafka, MQTT, for efficient data distribution among drones and ground stations. Adaptive clock synchronization implements PTP. PTP, as we know, is Precision Time Protocol or Network Time Protocol, NTP, with modifications for mobile airborne nodes. Uses GPS-disciplined oscillators on drones for initial synchronization, with local corrections based on inter-drone communications. Employs Kalman filtering to estimate and correct clock drifts in real time. Applications in different domains present unique challenges. For example, in agriculture, hyperspectral imaging for crop health assessment requiring high bandwidth data transmission and complex image processing. Precision spraying applications necessitating real-time decision-making based on processed sensor data. And in wildlife preservation, thermal imaging for animal detection and counting involving processing of large thermal data streams. Long-range operations in remote areas requiring efficient power management and possibly satellite communication integration. And in urban planning, LiDAR-based 3D mapping for infrastructure assessment, generating large point cloud datasets that need efficient processing and storage. Integration with existing urban data systems requiring standardized data formats and APIs. The primary challenges in implementing this system include ensuring service continuity during handovers or MAC relocations. That is to implement predictive handover algorithms that anticipate when a drone will move between edge computing zones. Use SDN, software-defined networking techniques, to dynamically reconfigure network paths during handovers. Employ state synchronization protocols to maintain application continuity when switching between edge nodes. Managing multiple communication routes with different latencies. That is to develop adaptive routing algorithms that can dynamically select the best communication path based on current network conditions and application requirements. Implement multi-path TCP, that is MPTCP, to simultaneously use multiple network interfaces, for example, cellular or satellite, for improved reliability and throughput. Use network coding techniques to enhance reliability and reduce latency in challenging network conditions. Energy efficiency. We need to optimize flight paths for energy conservation while maintaining sensing coverage. We need to implement dynamic frequency scaling on drone processors to balance performance and power consumption. use energy-aware task allocation algorithms to distribute processing tasks between drones and edge nodes in an energy-efficient manner. We can't leave here without talking data security and privacy, which is essential in all of these use cases. Implement end-to-end encryption for all data transmissions. Use secure enclaves or trusted execution environments on edge nodes for processing sensitive data. Develop access control mechanisms that can work in distributed dynamic environments. So by addressing all these challenges, the MEC-enabled geoservice sensing system aims to provide high-performance, real-time environmental monitoring and analysis capabilities across a wide range of applications, leveraging the unique advantages of aerial robotics and edge computing. So next we're looking at a picture or diagram that talks about MEC for geosurface sensing with aerial robots for use case 7. This diagram illustrates usage scenarios of edge cloud service for geosurface sensing data management. Let me break down the diagram a little bit, and then we can take a look at what is it telling us, or what is this about. So there are several system components here. First is the mobile edge computing clouds, MEC clouds. 2 are shown representing distributed edge computing resources. We have 6G RAN, the next generation radio access network. We have satellite, which is for global positioning and potentially data relay. We have 2 UAVs, drones, equipped with sensors. The ground station, which is depicted as a satellite dish, is also shown here. And various application scenarios like urban planning, wildlife preservation, and smart agriculture. For communication links, we have green lines representing communication links between various components. The blue cones likely represent sensing or data collection areas for the drones. So what are the key features here? Real-time coordination, validation, adaptation of fusion levels is highlighted, indicating dynamic data processing capabilities. Low latency feedback between MEC, mobile edge compute or multi-access computing, and ground station, emphasizing the importance of quick response time. What are the implications and associated technical details? The system incorporates aerial, that is drones, satellite, and ground-based sensing, allowing for comprehensive data collection across various scenarios. So this is what we call the multi-level sensing. MEC clouds, multi-access edge computing, clouds provide distributed computing resources close to the data sources, enabling low latency processing and reducing the need for constant communication with centralized servers. We're seeing 6G integration described here. The inclusion of 6G RAN suggests advanced wireless communication capabilities, likely supporting high bandwidth and low latency required for real-time data processing and coordination. The mention of real-time coordination, validation, adaptation of fusion levels indicates sophisticated data integration techniques that can adjust based on current needs and data quality. That's what we call the dynamic data fusion. The system is designed to support diverse scenarios, for example, urban planning, wildlife preservation, smart agriculture, etc., showcasing its versatility. This feature, the low latency feedback feature, enables quick adjustments and responses to changing conditions, crucial for real-time monitoring and control applications. Satellite technology likely provides global positioning data and potentially acts as a communication relay for areas without terrestrial network coverage. So it integrates with satellite networks. Drone coordination. The system appears capable of coordinating multiple drones, suggesting advanced swarm intelligence or distributed sensing capabilities. The architecture can scale from dense urban environments to remote agricultural areas, indicating a high, adaptable, scalable system. The emphasis on real-time coordination and low-latency feedback suggests the system can process and act on data quickly, essential for time-sensitive applications. As the title suggests, the data is designed for efficient management of geosurface sensing data, likely involving data storage, processing, and distribution strategies. The integration of various technologies, 5G, 6G, satellite, edge computing, implies a high degree of interoperability between different systems and protocols. The system can likely adjust its sensing strategies based on feedback and current conditions, optimizing data collection efficiency. So that's adaptive sensing. While not explicitly shown here, the use of edge computing and adaptive strategies likely contributes to overall energy efficiency, an important consideration for remote sensing applications. The mention of KPI, key performance indicator, characteristics suggests that the system is designed with specific measurable performance metrics in mind. So this diagram effectively illustrates a comprehensive geosurface sensing and data management system that aligns closely with the key points discussed in this particular 3GPP spec. It demonstrates how advanced communication technologies, edge computing, and diverse sensing platforms can be integrated to create a flexible, efficient, and powerful system for various environmental monitoring and management applications. The architecture emphasizes on real-time processing, low latency communication, and adaptive strategies, makes it well suited for the complex and dynamic requirements of modern geosurface sensing tasks. Use case 8. This is our last use case. Autonomous and teleoperated robots in mining. This use case examines the deployment of both autonomous and teleoperated robots in mining environments, a scenario that represents unique challenges due to the extreme and often unpredictable underground conditions. The robotic system encompasses various roles crucial to mining operations. What are the roles? Exploration utilizes advanced SLAM, again SLAM, remember, a simultaneous localization and mapping. SLAM algorithms adapted for underground environments with limited GPS access. Employs sensor fusion techniques, combining data from LiDAR, sonar, and potentially ground-penetrating radar for comprehensive environmental mapping. Drilling implements precise control systems for automated drilling operations, uses real-time vibration analysis and machine learning models for predictive maintenance and optimal drill bit usage. Hauling develops efficient path planning algorithms that adapt to changing mine layouts, implements V2X, vehicle to everything communication for coordination between multiple hauling robots and with other mining equipment. Inspection and maintenance utilizes computer vision and deep learning models for defect detection in mining equipment and tunnel structures. Implements augmented reality interfaces for remote human operators to guide maintenance robots in complex repair tasks. Environmental monitoring. It deploys a network of IoT sensors for continuous monitoring of air quality, temperature, and structural integrity. Uses edge computing nodes for real-time analysis of sensor data and early warning systems for potential hazards. So, what are some of the key features of this system? Key features include operation in extreme underground conditions, develops ruggedized hardware capable of withstanding high temperatures, humidity, and potentially corrosive environments, implements redundant systems and fault-tolerant software architectures to ensure continuous operation in harsh conditions. Combination of autonomous and teleoperated robots creates a flexible control architecture that allows seamless transition between autonomous operation and human teleoperation. Implements shared autonomy frameworks where robots can request human intervention for complex decision-making while maintaining autonomy for routine tasks. Enhanced communications and sensing networks. Deploys a mesh network of communication nodes throughout the mine to ensure consistent connectivity. Utilizes low-frequency radio systems for improved signal propagation in underground environments. Implements delay-tolerant networking protocols to handle intermittent connectivity. The primary challenges in implementing the system include maintaining reliable communication in challenging underground environments. Develops custom radio systems optimized for underground propagation characteristics. Implements advanced MIMO, MIMO stands for multiple input, multiple output techniques to improve signal quality in multipath rich environments. Uses cognitive radio technologies to dynamically adapt to changing RF conditions in the mine. Supporting energy-efficient mechanisms for multi-hop relay networks. Implements energy-aware routing protocols that balance network longevity with communication performance. Develops opportunistic networking techniques that leverage mobile robots as data mules to transport information between disconnected network segments. Uses wireless power transfer technologies to recharge communication nodes and sensors in difficult-to-access areas. Integrating MEC multi-access edge computing services for computationally intensive tasks. Deploys ruggedized edge computing nodes at key locations throughout the mine. Implements dynamic task offloading algorithms that consider both computational requirements and current network conditions. Develops edge native applications optimized for the specific computational and latency requirements of mining operations. Safety and emergency response implements real-time monitoring systems with AI-driven anomaly detection for early warning of potential hazards. Develops autonomous emergency response protocols for robots to react to dangerous situations without human intervention. Creates robust, redundant communication systems for fail-safe operation and emergency coordination. Integration with existing mining systems. Develops standardized interfaces for robotic systems to interact with traditional mining equipment and control systems. Implements data transformation layers to ensure compatibility between new robotic systems and legacy mining software. Long-term autonomy. Develops self-diagnostic and self-repair capabilities for robots to minimize the need for human intervention. Implements online learning algorithms for robots to continuously adapt to changing mine conditions and improve their performance over time. By addressing these challenges, the autonomous and teleoperated robot system for mining aims to significantly enhance safety, efficiency, and productivity in mining operations. This system represents a convergence of robotics, communication technologies, and data analytics, pushing the boundaries of what's possible in one of the most challenging industrial environments. Let's take a look at some diagrams for use case 8. This diagram here combines two figures illustrating extreme working conditions in mining sites and the integration of robotics and advanced communication technologies. So there's the top part and there's the bottom part. Let's take a look at the top part. Surface operations. It's depicting large excavator for digging and material removal, a tractor with front loader for material handling, dump truck for transporting extracted materials. Underground operations. 2 human figures shown working in tunnels. One figure operating a drilling machine, another pushing a cart, likely for ore transportation. So the bottom, let's take a look at the bottom part of the bottom figure. Let's take a look at the environment. Mountain range representing the mining site, division between geoservice and underground areas. Robotic systems, we have aerial drone for surveillance and data collection. We have ground-based mining truck for material transport. We have 2 underground robots for various mining operations. What about the communication infrastructure? We have RAN, the RAN tower, the radio access network tower for wireless connectivity. We have the MAC cloud, the mobile edge computing cloud for local data processing, and multiple wireless access points throughout the mining site. That's the communication infrastructure. For communication links, we have green zigzag lines representing wireless communication between various elements. So those are the different components. What are the implications that are shown here? Human replacement. The diagram shows the transition from human workers to robotic systems in extreme mining conditions, enhancing safety and efficiency. It's also showing multi-level operations. The system integrates surface and underground operations, requiring seamless communication and coordination across different environments. Integrated Sensing and Communications, ISAC in short. Robots are equipped with sensors represented by blue cones that likely serve dual purposes of environmental sensing and communication. We have multiple robots and communication points that create a distributed network for comprehensive data collection and information sharing. This is the kind of distributed sensing and communication that we've been describing in several of the use cases prior to this one. While not visually represented, the diagram caption mentions AI-enabled compute, likely facilitated by the MAC, the mobile edge computing, for real-time data processing and decision-making. So we have AI-enabled compute. The underground robots are described as capable of collaboration and group operations, suggesting advanced swarm intelligence or coordinated task execution. These are collaborative robots, so it's all about collaborative robotics. The various communication links imply the system can adapt to changing and challenging underground conditions, maintaining connectivity where traditional methods might fail. So adaptive communication is at play here. The MAC cloud enables edge computing, allowing for rapid data analysis and decision-making close to the data source. The aerial drone and distributed sensors can provide real-time environmental data, crucial for safety and operational efficiency in mining operations. The mining truck is shown operating without a human driver, indicating advanced autonomous navigation capabilities in challenging terrains. So it's doing autonomous vehicle operation. Multiple communication points suggest a redundant network design, crucial for maintaining operations in case of individual node failures. Network redundancy is designed into this picture. Cross-layer integration is depicted here by the system integrating aerial, surface, and underground operations, requiring sophisticated coordination and data fusion techniques. By replacing human workers with robots in extreme conditions, the system significantly improves worker safety in hazardous mining environments. The distributed nature of the system allows for easy scaling, adding more robots or sensors as the mining operation expands. While not explicitly shown, the comprehensive communication infrastructure suggests the possibility of remote monitoring and control of mining operations. Having all that said, what this diagram is doing is effectively illustrating the transition from traditional mining operations to a highly advanced, robotic-driven system. It showcased the integration of cutting-edge technologies such as robotics, AI, edge computing, and advanced wireless communications to create a safer, more efficient, and highly adaptive mining operation. The system's ability to operate in extreme conditions while maintaining robust communication and data processing capabilities aligns closely with the use case focus on enhancing operations in challenging environments through advanced robotic and communication technologies. Here's another program, also relevant to autonomous and teleoperated robots in mining. This diagram illustrates the phase difference caused between two antennas on a horizontal ground surface with different heights. Let's break down this diagram a little bit. What are all the system components shown here? First, we see a transmitter represented by a robot icon with an antenna. We have a receiver, which is another robot icon with an antenna. Geosurface, a horizontal line representing the ground. Obstacle, represented by a mountain-like shape between transmitter and receiver. So those are the four main system components. For key parameters, we have line of sight distance between transmitter and receiver. We have a horizontal distance between transmitter and receiver, and we have height difference between the two antennas. We have the angle of incidence or angle of reflection. And we have some other additional parameters mentioned but not explicitly defined in the diagram. So those are the few parameters indicated by some letters, small case letters. In terms of the signal paths, for the blue line, that is a direct path, represents the line of sight transmission. We have the orange line, that's the reflected path, which shows the signal reflection off the ground surface. Let's take a look at what this is all telling us. It's telling us multi-path propagation is possible. The diagram illustrates two signal paths, direct and reflected, which is crucial in understanding the phase difference phenomenon in wireless communications. We also see phase difference. The main focus of this diagram is to show how the height difference between antennas leads to a phase difference between the received waves. This phase difference is due to the different path lengths of the direct and reflected signals. In terms of geometric relationships, the line of sight distance, L, is longer than the horizontal distance, D, due to the height difference, H. Those are the letters that are showing the different, what they refer to. The reflected path is even longer, contributing to the phase difference. Angle of incidence reflection, so that angle sign, like an O with a line in the middle, represents both the angle of incidence and reflection, following the law of reflection, where these angles are equal. In terms of ground reflection, the reflection off the geosurface can cause constructive or destructive interference at the receiver depending on the phase difference. The diagram emphasizes how different antenna heights affect signal propagation, a crucial consideration in designing robust communication systems for varied terrains. While not explicitly shown, the presence of the mountain-like obstacle suggests the importance of considering Fresnel zone in line-of-sight communications. So Fresnel zone consideration. Complex environment modeling. This simplified model helps in understanding signal behavior in complex mining environments where obstacles and varying terrain are common. The phase difference can significantly impact signal quality and strength at the receiver, affecting overall communication reliability. So there's this signal quality implications that we need to consider. Understanding this phenomenon allows for adaptive positioning of antennas to optimize signal reception in challenging environments. So the phenomenon I'm referring to is the adaptive antenna positioning. Diversity techniques. This model can inform the design of diversity techniques to mitigate the effects of multipath fading in mining communications. How do we do robotic communication optimization? For robotic systems in mining, this understanding helps in optimizing robot positioning and antenna design for better communication links. For environmental adaptability, the model suggests the need for communication systems that can adapt to varying terrain and obstacle configurations in mining operations. Interference prediction. By modeling these phase differences, the system can predict and mitigate potential interference issues in complex mining environments. And we need to do link budget calculations. This geometric model is crucial for accurate link budget calculations, ensuring reliable communication in various mining scenarios. This diagram effectively illustrates the complexities of wireless signal propagation in mining environments. It highlights the importance of considering factors like antenna height, ground reflection, and terrain obstacles in designing robust communication systems for extreme working conditions. The model provides a foundation for understanding and addressing challenges in maintaining reliable wireless links for robotic and automated systems in mining operations, aligning with the use case focus on enhancing communication capabilities in challenging industrial environments. Here's another diagram relevant to use case 8. This diagram illustrates two types of serially connected multi-hop networks. The first one is what we call the conventional serially connected multi-hop network. That's A, we have A and we have B, the top and the bottom. So A is the conventional serially connected multi-hop network. There are 3 robot icons shown in a linear arrangement. Each robot has a blue cone representing its sensing or data collection capability. And the green zigzag lines connect the robots, indicating wireless communication links between adjacent nodes. B, the bottom the bottom half of the diagram shows non-conventional serially connected multi-hop network with a supplementary link, similar to A, but with an additional pink arrow connecting the first and third robots. This pink arrow represents a supplementary link described as being supported when cooperative diversity is applied. What is it implying here? It's implying a multi-hop architecture. Both configurations demonstrate a multi-hop network where data is relayed through intermediate nodes to reach its final destination. This is particularly useful in environments where direct long-distance communication is challenging, such as underground mining operations. The blue cones suggest that each robot is equipped with sensors, likely for environmental monitoring, obstacle detection, or data collection relevant to mining operations. So there are sensing capabilities. The green zigzag lines represent short-range wireless communications between adjacent robots. This could be using technologies like Wi-Fi, Bluetooth, or specialized short-range communication protocols suited for harsh mining environments. In both configurations, the middle robot acts as a relay, receiving data from one end and transmitting it to the other. This extends the overall communication range of the network. So it has relay functionality. Conventional versus non-conventional, I use those two terms. The key difference between A and B is the supplementary link in the non-conventional setup. The supplementary link in B is described as being supported when cooperative diversity is applied. Cooperative diversity is a technique where multiple nodes collaborate to improve the reliability and efficiency of wireless communication. The supplementary link in B provides a redundant path for data transmission, potentially improving the network's reliability and resilience to individual link failures. So it provides redundancy and make it more reliable. The ability to establish supplementary links suggests an adaptive networking capability where the system can reconfigure its communication paths based on current conditions or requirements. While not explicitly shown, the multi-hop architecture can contribute to energy efficiency by allowing nodes to communicate over shorter distances, potentially using less power for each transmission. The multi-hop design is inherently scalable, allowing for the addition of more nodes to extend the network's reach or coverage. In the conventional setup A, latency may increase with each hop. The supplementary link in B could potentially reduce end-to-end latency for some communications. The non-communication setup may require more sophisticated interference management techniques due to the overlapping communication paths. The ability to establish supplementary links demonstrates the network's flexibility in adapting to different environmental conditions or communication requirements. So we must adjust or accommodate network flexibility. This network architecture is well suited for mining environments where line-of-sight communications may be limited, and a flexible, resilient communication network is crucial for safety and operational efficiency. In both setups, intermediate robots or intermediate nodes could potentially aggregate data from multiple sources before relaying it, optimizing bandwidth usage. This diagram effectively illustrates advanced networking concepts applicable to extreme working conditions like those found in mining operations. It showcases how robotic systems can form flexible, resilient communication networks in challenging environments, leveraging techniques like multi-hop relaying and cooperative diversity to maintain reliable communications. Here's another diagram that illustrates some examples of set of multi-hop UE relays of robots at underground mines. What are we looking at here? We have a set of multi-hop UE relays. It indicates the underground segment, that's the tunnel, represented by a yellow rectangle. That's the environment. For components, we have multiple robot icons representing UE relays, user equipment relays. Each robot has a blue cone indicating sensing or data collection capabilities. We have a tunnel exit symbol. We have RAN tower, which is the radio access network tower, and mobile edge computing cloud. Those are the components. For communication links, we have green zigzag lines between robots indicating wireless communication links. For data flow, we're seeing bidirectional arrow between below, indicating data flows. That is multimodal, multi-flows, multiple QoS requirements. In B, we are seeing a set of 3 sets of multi-hop UE relays in 3 tunnel branches. So for the environment, there are 3 parallel tunnels represented by yellow rectangles. For components, we have multiple robot icons in each tunnel. We have the tunnel exit symbol and 5G RAN tower. For communication links, there are implied wireless links between robots, which is not explicitly shown here. Yellow arrows indicating connections between tunnel branches. So let's take a look at what the technical details and implications are. This is a multi-hop UE relay architecture. Both scenarios demonstrate a multi-hop relay system where robots act as UE relays, extending network coverage deep into underground mines. Scenario B shows how the system can adapt to complex mine structures with multiple branches, ensuring comprehensive coverage. So we have adaptability to mine layout. The mention of multimodal data flows suggests the system handles various types of data, for example, sensor readings, video feeds, control signals, etc., simultaneously. So that's multimodal data. We have multiple QoS requirements. The system supports different quality of service levels, likely prioritizing critical safety data over routine operational data. And we have bidirectional communication. The bidirectional arrow implies two-way communication, essential for both data collection and remote control of robots. The presence of MEC, multi-edge computing, indicates local processing capabilities, reducing latency and bandwidth requirements for time-sensitive operations. In scenario B, the interconnected tunnel branches suggest potential for routing redundancy, enhancing network reliability. The design allows for easy expansion by adding more UE relays as the mine extends or new branches are developed. So scalability is considered. The multi-hop architecture effectively extends network coverage into areas where direct communication with a service would be impossible. Short-range communications between adjacent relays can be more energy efficient than long-range transmissions to a central point. The system likely employs adaptive routing algorithms to optimize data flow through the network based on current conditions. The blue cones on robots suggest integrated sensing capabilities, allowing for environmental monitoring throughout the mine. This communication infrastructure supports real-time monitoring and rapid response to potential safety issues in the hazardous mining environment. The multi-hop architecture allows for frequency reuse, improving overall spectrum efficiency in the confined underground space. While multi-hop systems can introduce latency, the integration with MEC helps manage this by processing time-sensitive data closer to its source. In the multi-branch scenario B, careful frequency planning and interference management would be necessary, especially at branch junctions. The interconnected nature of the network, especially in scenario B, provides resilience against individual node failures. So this diagram effectively illustrates advanced networking concepts for underground mining operations. It showcases how robotic UE relays can create a flexible, resilient, and comprehensive communication network in the challenging underground environment. The system's ability to handle complex data requirements, adapt to mine layouts, and integrate with edge computing aligns closely with the use case focus on enhancing robotic operations and communications in extreme industrial settings. This architecture addresses the unique challenges of underground communications while supporting the diverse data needs of modern mining operations. All right, we have gone through 8 use cases. So beyond the specific use cases we've explored, there are several overarching themes and technologies that are crucial to the future of service robot networks. What are they? Tactile and multimodality communication, TACMM in short. This emerging field aims to enable more natural and intuitive interactions between robots and humans. TACMM, tactile and multimodality communication, involves the transmission of touch and other sensory information, potentially allowing for remote operation with a sense of physical presence. This could revolutionize applications like telemedicine or remote industrial operations. We have ISAC, short for Integrated Sensing and Communication. ISAC represents a paradigm shift where communication systems also perform sensing functions. For robots, this could mean using communication signals for environmental mapping or object detection, improving efficiency and reducing hardware requirements. Metaverse aspects related to robot applications. As the concept of the metaverse evolves, robots could serve as physical avatars or interfaces to virtual environments. This integration could enable new forms of remote presence and interaction, bridging the physical and digital worlds. High-level communication scenarios. We need to consider various communication pathways for robots. Robot to robot, R to R, direct communication between robots for coordination and data sharing. Robot to infrastructure, R to I, interaction with smart city infrastructure, traffic systems, etc. Robot to pedestrian, R to P, communication with humans in shared spaces, crucial for safety and social integration. Robot to network, R to N, access to cloud services, updates, and centralized control systems. R2C, robot to cloud, offloading of computationally intensive tasks and access to vast data resources. Robot to grid, R2G, interaction with power systems for efficient energy management and charging. Robot to home, R2H, integration with smart home systems for domestic service robots. Each of these communication scenarios presents unique challenges and opportunities, requiring careful consideration in network design and protocol development. So this diagram illustrates an example of topology studied within 3GPP Release 18. TACMM, single hop connections only. I wanted to present this quickly because this diagram originates from 3GPP Technical Report 22.847, which is a separate technical report, a spec altogether, but it is relevant. So I'd like to break down the technical details a little bit and quickly. This is a simple diagram. What are the system components shown here? We have 5G UE, which is a pair of VR glasses, virtual reality glasses, or a virtual reality headset. We have 5G UE, which is a pair of gloves, 2 haptic gloves. 5G network represented by a cellular tower icon. and application server, a server for processing and managing application data. For connections, we have blue lines representing service data flows from the UEs to the application server through the 5G network. What is it implying here? We have 5G connectivity. Both the VR glasses and gloves are 5G enabled UEs, capable of high-speed, low-latency communications essential for immersive XR experiences. XR is extended reality experiences. It's indicating a single-hop architecture. The diagram specifically notes single-hop connections only, indicating direct connections between UEs and the 5G network without intermediate relays. The combination of VR glasses and haptic gloves suggests a multimodal XR system. XR again is extended reality system, integrating visual and tactile interfaces. In this kind of applications, there are low latency requirements. XR applications, extended reality applications, especially those involving haptic feedback, require extremely low latency, which 5G networks are designed to provide. The service data flows are shown from UEs to the application server, indicating uplink traffic, and it emphasizes the importance of robust uplink capabilities in 5G for XR applications, because usually uplink is heavy traffic going uplink on the uplink's direction. While not explicitly shown, the proximity of the application server to the 5G network in the diagram suggests potential edge computing capabilities for reduced latency. The system must maintain tight synchronization between the VR glasses and gloves for a coherent user experience. So synchronized multi-device operation is required. VR operations or VR applications typically require high bandwidth, especially for high quality visual content, which 5G networks are well suited to provide. The 5G network must manage different QoS requirements for visual and haptic data streams. The diagram showcases the seamless integration of XR devices with 5G networks, a key focus of TACMM. Again, TACMM is Tactile and Multimodal Communication Studies. While not shown, 5G networks can employ network slicing to optimize resources for different XR service requirements. The single-hop topology suggests a focus on optimizing direct device-to-network connections, which is crucial for scaling XR services. For uplink-downlink asymmetry, XR applications may have different requirements for uplink, for example, user inputs, environment scanning, and downlink, for example, rendered visuals, traffic. There are energy efficiency challenges. Maintaining continuous high-speed, low-latency connections for XR devices poses energy efficiency challenges that 5G networks must address. So there's security and privacy, of course, that needs to be considered. The direct connection of personal XR devices to the network emphasizes the need for robust security and privacy measures. The diagram effectively illustrates a basic topology for XR applications leveraging 5G networks. It highlights the direct integration of advanced XR devices with 5G infrastructure, emphasizing the potential for high-performance, low-latency applications. The topology presented here serves as a foundation for understanding more complex XR scenarios and their network requirements in future mobile systems. All right, conclusions. As we conclude our exploration of networks of surface robots with ambient intelligence, it's clear that this field represents a convergence of multiple cutting-edge technologies and presents both significant opportunities and challenges. Let's summarize our key findings and look towards future developments. Here's a summary of key findings. Diverse applications. We have seen that service robot networks have potential applications across a wide range of sectors, from smart communities and healthcare to industrial operations and environmental monitoring. This diversity underscores the transformative potential of these technologies. Technological convergence. The successful implementation of service robot networks requires the integration of various technologies.